Okay, guys, quick corollary to this problem. I just wanted to come back real quick and revisit the DQ, the way we had defined DQ. And the reason is that normally I lose some folks there when it comes to that. So I'm talking about this, the way we define DQ. This is an important aspect of solving these problems. And the advice I gave you first time through was to think about dimensions. But there's some other notes I want to make real quick. And one is that notice that this DQ here, we're writing in terms of lambda and dx. Okay, cool. So I want to talk about motivation a little bit more. So one is that dx is part of the properties of our differential element. So our differential element is a tiny little point charge, right? It's a chunk of charge. We know that it has an amount of charge dq on it. I can also say that it has some length that I can call dx. So like every little chunk of charge is going to have some length, non-zero length, that I can call dx. And when I add up all of those dx's, I can add them up in order to make my charge distribution L. So you might be wondering, so why like the obsession with x, right? Why are we like super into x right now? Okay, so here's why. This is physical motivation. Look at the thing that we're trying to integrate. And this is, I'm trying to give you general advice on this. So we're trying to find electric field. So you dig into your physical situation and you ask yourself, first of all, like, why are you even integrating? What's changing? What is it that's necessitating the integral? So here you might answer. So pause and think about that for a second. And one of the ways you might answer that is that every little different DQ along this rod, every little different DQ contributes a different DE, right? That as I move DQ along the rod, DE changes. It changes in magnitude because DQs are going to be different distances from P, right? We have some symmetry, so everybody will have one other DQ that's the same distance. But even so, that other one um, will have a different direction. So what really is driving the need to integrate is the fact that my DEs are changing, right? Okay, so then let's carry that on further. Why are the DEs changing? The DEs are changing because I'm moving along X. As I move along X, DE changes. So phi changes too, right? There sometimes you can kind of see a few different things in a problem that change. And then it might be a little confusing, like, well, how do I know what to integrate with respect to? So, my answer to that question is usually what is the most fundamental thing that's changing that's causing the need for integration? So, and I'll try to give you more advice on that as we move into these different examples. But this is the stuff that for most people, they did not really talk about in this way in math. So right now is the first time that you're coming across making these decisions. Like, how do I know how to switch out what I'm integrating with respect to? And in math, how they might have talked about that is like changing the variable that you're integrating with respect to. And how I want you to think about it now in physics is which characteristic of this system am I going to integrate with respect to? What physical characteristic? If you don't have an eye on that or you don't really understand that, then you're not solving a physics problem. You might be doing some math, but you're not solving a physics problem. So keep an eye on that. This is the simplest intro to that, and that is this for this one-dimensional distribution. But we'll talk about that every time. And every time you do a charge distribution problem, you're going to go through these steps of define DQ, and I encourage you to do them in this order. Define R, and then you'll define your surviving component. And then you use those three things to put your integral together.